Hello, Namaskara. Welcome to again the e-Shikshan under the umbrella of VTU. I am PR Hampioli, Head Department of Mathematics, KLS Gokte Institute of Technology, Belgavi. Dear students, we are discussing one of the modules of Engineering Mathematics 3, 18 Math in 31, 18 Math 31, that is Fourier transforms and Z transforms. We are in the ninth lecture of this module and third lecture of Z transforms. So I think you are ready with your pen and pad. I always request you to be ready with your pen and pad because if you write along with me, you'll be more used to the formulae. You will more be used to the symbols, and you'll be more used to what to write instead of just observing it. So here we go to the lesson number 9. Lesson 9 of module 3 of engineering maths 3, that is the 18 math 31. So we are studying now Z transforms at present. So now quick revision again, very quickly. We defined any function of n we can transform into some function of z via the transform known as Z transform, a capital big Z I write, by multiplying this n function by some z function. My dear students, I told you can go on choosing this. If at all you want to create your own transform, you can create your own transform by choosing different weight functions, kernel of functions. So there are many transformations. After all, basic need of transformation is we cannot do the work in time domain. For example, in n domain, we'll transform to some frequency domain like Z transform. Especially I am talking in view of signals in the system, suppose in communication theory, in electronics. Then n will be changed to Z language and the work will be done in Z language. At the end, the answer is transformed by taking inverse transform into n language. So now that is the basic. Coding is done. In a coded language, the work is done. At last, the answers or output is decoded. Now, this is added from n equal to 0 to infinity. We should not forget that this value of u is 0 for u minus 1, u minus 2, u minus 3 and negative suffixes of n. Afterwards, using this definition, first we found Z transform of a raised to n using the formula. It reduced to geometric progression. So using that, we got it as Z by Z minus a. So we got familiar using this formula. Instead of a, you can go on writing 2 raised to n. Instead of a, 3 raised to n. So on and so forth. You can write. So instead of a, you should write here 2. Z by Z minus 2. So instead of 2, you will get 3 here. Z by Z minus 3. So I can go to negative suffixes also. So next example, z raised to minus 2 raised to n. So this was plus 2 raised to n. So z minus 2. So this becomes z plus 2. So if I put a equal to 1, basics we should not forget. Many times z transform of 1 will have to use, which becomes z by z minus 1. But whereas interestingly, because it is many times misunderstood or not written properly. Instead of plus 1, if I write minus 1 please, then that is, instead of z minus 1 here, it becomes z plus 1. Now continuing this part little more. So we have also proved that instead of 1 here, some constant, if I write Z transform of 8, it becomes, you can take 8 out and Z transform of 1, which is 8 times Z by Z minus 1. In general, for a k constant, Z transform of K is K into Z by Z minus 1, where some K is a real constant, number, any number you like. So that if at all I write, it can be, this can be fractions also. These can be fractions also. For example, if at all you want to take these things as fractions, what happens is let me choose black from this. If at all we take, suppose the Z transform of some fraction, half raised to n, Z transform of half raised to n, or Z transform of half, suppose instead of K, half. So half into Z by Z minus 1. Furthermore, here I was talking instead of 2 raised to n, 3 raised to n, if I write it as some 3 by 2 raised to n, so it is Z by Z minus 3 by 2. It is all question of getting used to it. That's why I'm rewriting Z transform of, if I write minus sign to that 3 by 2 raised to n, and that becomes Z by instead of minus 3 by 2, that becomes plus 3 by 2 plus 3 by 2. So furthermore, we also studied that, so don't forget Z of 1, Z of 1, Z of constant, Z of 1, don't forget, Z of minus 1, don't forget, Z of K, don't forget. So don't forget many things. That means you be familiar to that. I don't tell you remember, you be familiar. So now using this Z of using this today's example starts. Using this Z of A raised to n equal to Z by Z minus A, Z by Z minus A. Let me prove some important examples. Find Z transform of cos hyperbolic n theta and sine hyperbolic n theta. So we have proved instead of hyperbolic simply cos n theta, sine n theta, and amazingly these also look same, but we'll be using this as well as the basic definition of cos hyperbolic n theta. I'll do this, and similarly I'll give this homework to you. Now cos of hyperbolic of something is e raised to that plus e raised to minus that divided by 2. Now we will be using some basic laws of indices learnt in school also. Please, all the things what you learned basics will be now and then will be useful. So now if I take Z transform on both sides, find Z transform on both sides, Z transform on both sides. So whatever is left hand side, Z of this, and whatever is right hand side, Z transform of that. Z transform means n language, we are trying to convert in terms of Z language. Now right hand side, if I concentrate, I can take half out. These are all come under linearity property. I can take Z transform of first function. I can drag this Z transform inside, Z transform of first function. Second one is Z transform of second function. So that I can write this as Z transform of first function e raised to n theta, this plus Z transform of second function e raised to minus n theta. So here we use basic laws of indices. Z transform of this can be written as something raised to n, which is e raised to theta raised to n. It becomes n theta only. Plus this also can be written as something raised to n, so that this remaining e raised to minus theta sits here, Now, what is the variable? See here, variable is n. So if it is not n, which is not n, that is theta acts as a constant. So this inside whatever is there, these two act as constant. Something like z of a raised to n. So this a is a constant. This a is a constant. So instead of a, now what is the formula for z of a raised to n? Today only I wrote z by z minus a. So instead of a, I'll be writing e raised to theta here and e raised to minus theta here. So here we go, half of, this is z by z minus a. Here a is e raised to theta, and here z by z minus, again a is e raised to minus theta. So now we have converted in terms of z language. Remains is just algebraic simplification. I can drag this z out. So z by 2, I can cross multiply these two. So z minus, so it looks like this now, 1 upon z minus e raised to theta plus 1 upon z minus e raised to minus theta. Now usual simplification, LCM, simplify. This is equal to z by 2. Cross multiply for the LCM. So z minus e raised to minus theta plus z minus e raised to theta. So when I cross multiply, what I am going to get here inside, this is equal to z by 2 as it is z plus z 2 times z minus into bracket exponential functions. So denominator z square and z term. So z term is 1 here and z term is 1 more here. So if we take z common, you will get e raised to theta, e raised to minus theta. So both having negative sign, e raised to theta plus e raised to minus theta. Back you can see minus z e raised to theta and minus z e raised to minus theta. Remains is multiplication of these two, e raised to theta, e raised to minus theta become e raised to 0, 1, minus of minus plus 1 with a little algebra. So you were taught algebra from 7th standard. So everything will be useful. Now we'll have to come to the basics again. See, what is cos? What is cos hyperbolic? What is cos hyperbolic theta? E raised to theta, e raised to minus theta divided by 2. This numerator is there here. So we need divided by 2. Here I'll drag this half out inside. Here I'll drag this half inside. So 2 and 2 getting cancelled. Z as it is minus e raised to theta plus e raised to minus theta divided by 2. So numerator no problem. Denominator, there is no 2 here. So multiply and divide. So whatever you want, get it. Z square minus z multiply by 2 and divide by 2, which is e raised to theta plus e raised to minus theta plus 1. So here is the completion of z transformation of cos hyperbolic function, which is with little simplification z into bracket z minus, it is exactly same structure without hyperbolic, without h. If you go on removing this h, same thing you get, z square minus this 2z will remain, 2z cos, see here we go, cos hyperbolic theta plus 1. So let me apply just a note, as a note, let me apply a damping rule. So if I multiply a raised to n to this inside whatever is there, if I multiply a raised to n to this cos hyperbolic n theta. Then wherever z is there, z by a, z by a, z by a, z by a, you have to go on writing, which is if I write the structure as it is, z minus cos hyperbolic theta. See, after transformation there should not be n here. That is very basic, because the basic definition is n function we are transforming to z function. So this square minus 2z cos hyperbolic plus 1, but because of change in the domain, the change in the codomain is you have multiplied here, you have to divide here, you have magnified here, you have to contract and reverse it back. So these things are taken into many relay functions, TV functions, all these things. So remaining is if you simplify, taking LCM and all that, this looks like this: z square, z into z minus a into cos hyperbolic theta whole divided by z square minus 2az plus a square. Very similarly, try to prove using the formula, sine hyperbolic theta is e raised to theta minus e raised to minus theta by 2. Using this formula on the same lines, you prove that z sine hyperbolic n theta, that is z transform of sine hyperbolic n theta, should be z into sine hyperbolic theta divided by z square, denominator same, z square minus 2z sine hyperbolic theta. The previous we left something, let us see that, plus 1. See here what we left in the previous, this cos hyperbolic theta we left here, please correct cos hyperbolic theta multiplication here. Now again, using damping function, you can prove that if I multiply by a raised to n, this looks like this. This looks very similar to. So use wherever z is there, you put a by z, az sine hyperbolic theta whole divided by z square minus 2az. This is again cos hyperbolic theta. Denominator is not changing. Minus 2az cos hyperbolic theta plus 1 plus a square here. So these two you can prove. Now very similarly, using basic functions and all that, let us have some more important examples, some more for practice, for examination point of view, some more important examples, which is revising all the things what you have learned, and furthermore we'll go one step ahead. First example, can you find z transformation of half raised to n plus 1 by 3 raised to n? I think many of you can. Now z transformation of first function plus second function is equal to z transformation of first function plus z transformation of second function. So now we know that z transformation of a raised to n is z by z minus a. So using this formula, so here also this is our a in the formula. So a raised to n. So wherever a is there, half here and 1 by 3 here. So shall we do that? So left hand side, z transformation of this raised to n plus this raised to n, that is half and 1 by 3 raised to n equal to z by z minus a. Here a is half plus z by z minus a. So remains the simplification. Why not? We should do the simplification. So algebra. So this 2 comes here. 2z minus 1. This divided by 2 I'll write here. Similarly, 3z minus 1 divided by 3 I should write here 3z. Now again, if I take this z common, 2 by 2z minus 1, let us do it simple, 3 by 3z minus 1. Now you know the LCM pattern from school level again, z into, so these two multiplications in the denominator and this cross multiplication, which is 2 times 3z minus 1 plus 3 times 2z minus 1. So you can expect that z term, constant term, so that if I multiply this equal to z into denominator as it is, or denominator also you can multiply z square term, z term minus 2z and minus 3z minus 5z, constant term minus of minus plus 1. So here 6z plus 6z, this becomes a 12z. Then minus 2 minus 3 minus 5. Shall we write this as the answer? At the most you can multiply z inside. What we did, my dear students, we applied this formula. So applying that formula, wherever a is there, z by z minus a. So linearity property, z transform of first function plus z transform of second function, that made us to write, and little bit of algebraic simplification. So we got this. Shall we go to the next one? Very similar. One more. Next one. Z transformation of. Can you do this example? 4 raised to n plus 8. They are simple. Just you have to remember the formula. Now find Z transform of this. Now the solution part, Z transformation of 4 raised to n plus 8. First thing is using linearity property. Z transform of, just like derivative of first function plus derivative of second function. Sorry, Z transform of these two separately. Again using Z transform of a raised to n equal to z by z minus a. So in this case a becomes 4. And again using Z transform of a constant is kz by z minus 1. Here k becomes 8. So Z transform of 4 raised to n plus 8 looks like this. Z by z minus 4 plus 8 into z by z minus 1. You have done it. At the most you can simplify, not to worry that. So some more examples which gives us practice. Suppose I do next example like this. Okay. Find Z transformation of cos of, not hyperbolic, cos of n pi by 2 some n function plus some constant pi by 4. So I have to recall some formulae here. First of all, what formula I'll recall is two formulae. One is cos of n theta z transform of that. So what is the corresponding z function? This is n function. Corresponding z function is z into z minus cos whole divided by z square minus 2z cos theta plus 1. So here it is n theta. So this becomes theta. Theta is pi by 2. Also we have to recall. Okay, we have to recall cos of a plus b, cos a cos b minus sin a sin b. That is, these A and B are here. Cos A, cos B minus sin A, sin B you have to apply. So with these two formulae we are ready to find. Okay, similarly sign of this you can do as a homework. So in the previous example, did I give you the homework? No. Let us see. I'll come back to that. So yes, I had given this homework. Without fail you do this. Without fail you do this. Now, coming back to this. Z transformation of cos of something like A plus B. Cos of A plus B is cos A cos B minus sin A sin B. So corresponding A and B, cos A cos B, cos A cos B, sin A sin B, with little attention. Now Z transformation of this, I should not forget this Z, I should not forget to write, so that both sides is equal to Z transformation of this, because only the expansion of this equal to this is written. Right hand side, so Z transformation of first function plus Z or minus Z transformation of second function. So can you write that this is a constant, cos of pi by 4, which is 1 by root 2. So 1 by root 2 Z transformation of cos n theta, theta is pi by 2, minus sin n pi by 4 also, this is 1 by root 2, this is 1 by root 2, write it 1 by root 2, and afterwards Z transformation of sine, Z transformation of sine of n pi by 2. So we have to recall Z transformation of sine n theta also. So if it is Z transformation of sine n theta, can you recall it? Denominator is same. Z sine theta divided by denominator same. Z square minus 2Z cos theta plus 1. So now using these two formula, wherever theta is there, pi by 2, pi by 2, pi by 2, you have to go on writing, because n theta, this is theta, n theta, this is theta. So that please see, observe 1 by root 2 corresponding Z function after transforming, no n, only Z, Z into bracket Z minus cos theta, theta is pi by 2, whole divided by Z square minus 2Z cos theta, theta is pi by 2. So plus 1. So what I applied, wherever theta is there, n pi by 2, so here pi by 2, so wherever theta is there, pi by 2, pi by 2, I went on writing. Similarly here now I have to write, wherever theta is there, pi by 2, pi by 2, pi by 2, I have to go on writing. So this becomes now minus of 1 by root 2 Z transformation of this Z sine theta, theta is pi by 2, whole divided by denominator is same. So let me write Z square minus 2Z cos of theta plus 1. Now wherever cos pi by 2 is there, we will have to write 0. So Z transformation of LHS looks like this. 1 by root 2 if I write common, this 1 by root 2 if I write common, this becomes 0. So Z into Z, Z square remains, whole divided by Z square. This is 0, 0 here, plus, so this is 0, Z square plus 1 is remaining, that is first one, minus sine of pi by 2 is 1, so minus Z is remaining here, whole divided by Z square plus 1. As the denominators are same, you can add up the functions. They look like this. Z transformation of Therefore, cos of n pi by 2 plus pi by 4 at last is 1 by root 2 common denominator numerator z square minus z is the final final answer. So this is the final answer. So why not? You should try z transformation of sine of n pi by 2 plus pi by 4. Very similarly, you try this without fail. So now we are doing this to revise our previous knowledge. Next example in the same lines. Find can you do this? Z transformation of n upon 3 raised to n plus 2 raised to n square. So let me revise all your Z transformations of the type Z of n, Z of n, Z of n square, Z of n cube, Z of n raised to 4. Let me take a pause. Can you write it? Can you write it? First, z by z minus 1 raised to 2. Second, z square plus z by z minus 1 raised to 3. Third, z square plus 4z z cube plus 4z square plus z by whatever is there, this raised to 1 extra 4. So here 1, here 2, here 2, here 3. Denominators are always same, z minus 1 only. But if it is 4 here, this becomes 5. And only the numerators, if it is raised to 4, it starts from raised to 4 and goes on decreasing up to z. You have to only remember these coefficients. So which I'll repeat the coefficients now. 11z square plus z. So what are the coefficients you have to remember? Here the coefficient of this is 1 z. Here the coefficients are 1 z square plus z. Here the coefficients are 1 z cube plus 4z square plus z. Here the coefficients are 1 1 z raised to 4 plus 11 z cube plus 11 z square plus 1. Now especially n and n square are useful. Now I'll come back to the example after this basics. So we got revised, we remembered these formulae. Now we are asked to find z transformation of, I'm rewriting, n by 3 raised to n. Instead of 3 it may be 6, no problem. And 2 raised to n square, instead of 2 it may be some 10, no problem. First of all, linearity property, z transformation of first function plus z transformation of second function, which is n by 3 raised to n, 2 raised to n into n square. Now first let me consider z transformation of n, which just now I wrote the formula. Z transformation of n is here, z by z minus 1 whole square. So shall I write? So here we are applying the damping rule also. So let me remind you, if at all I divide by, means z by 3 raised to n, which sometimes is taken as z transformation of 3 raised to minus n into, sorry, here it is n. So this change, wherever n is there, you multiplied or divided by 3 raised to n. So if you divide here, this side you have to multiply. That is, this 3 makes it 3z. If it is 4, it makes it 4z. See this? So what the changes are there? First I'll write the structure as it is. First, I'll write the structure as it is, which is, so because of this change 3 raised to n, this 3 makes it 3z. So first one I found. Now second one. So let me consider it as RHS, okay, and this as 1. Now consider again Z transformation of. Second one here, n square. Just now we wrote the formula. N square means start from z square plus z something raised to 3. So z minus 1 raised to 3. Now, if it is n square, if I make the corresponding change, for the corresponding change usually first I write structure as it is, then let us incorporate the changes later on. Z square plus z. So same thing I am writing, z minus 1 whole cube. So what is the change we are doing here is we are magnifying it, multiplying. So correspondingly reverse function will have to divide here with little simplification which we have done many times taking LCM. This starts looking like this now. So this is 2z square plus 2 square means 4z whole divided by z minus 2 whole cube. Now we found both of these. One is z transformation of 2 raised to n into n square, which I call it as 2 result, and even one result number 1. Result number 1 and 2 we incorporate in RHS, so that whatever is asked we are going to get. Z transformation of therefore n by 3 raised to n plus 2 raised to n square. The first one was, if you recollect, 3z minus 1 whole square. If you practice, it is not difficult. Please practice many times and telling. Be used to it. Be familiar to it. Again and again do it. Okay. See how many times you have sung Janagana Mana. Can you forget it? So why not? You can practice many things which you have to do in the life. Practice it so that they become part of your life. They become tip of your tongues. So let us go ahead. Second one we found in the above part here, 2z square plus 2 square z whole divided by z minus 2 whole cube. All these things, my dear friends, we did for some practice. Very similarly, please go ahead with some more functions. Find the z transformations of e raised to n sine 2n n theta. First you find sine n theta, then damping rule. Okay. Second one a raised to n e raised to minus a divided by n factorial. So this e raised to minus a is a constant. So first find 1 by n factorial, then use the damping rule. So with this we are ready to go ahead for the next observation. Before we go for the next observation, always I tell that for the next concept, again first let us observe. After observation I want you to write some rules which I shall help you. First of all, suppose I am in a n function. So I am trying to tell you notations. So if I change n here, correspondingly n should change. That is shifting I am doing. So if I change n to n plus 1. Correspondingly, wherever n is there, so wherever n is there, n plus 1. If I go on writing, the corresponding change will be n plus 1. So similarly, if I write un plus 2 is wherever n is there, n plus 2, so on and so forth. In general, suppose if in general, what is un plus k? So I am moving k steps ahead. This is n plus k whole square. This n square is just for namesake, naam ke vaste. Instead of n square, n cube, cube, here cube, here cube. Similarly, I can write negative suffixes also here. For example, if it is n minus 1, it should be n minus 1 here also. So let us get, we are getting used to the notations. N minus 2, n minus 2 whole square. In general, n minus k, n minus k whole square. So can you help me to write one more example then? Can you help me to write one more example? We can take any n function, whatever you like, something in n you write. Suppose I write 1 by n factorial. So can you help me to write n plus 1? Wherever n is there, you write n plus 1. But these symbols help us a lot because mathematics is a language of symbols. So on and so forth. In general, n plus k is 1 by n plus k factorial. Can you have negative here? un minus 1, un minus 1, 1 by n minus 1 factorial. Un minus 2, 1 by n minus 2 factorial. In general, un minus k, 1 by n minus k factorial. So we are getting used to some changes in suffixes en, but which help us for this one now. What is the meaning of this? Shifting un. We are shifting un either to the right side or left side. Suppose if I write un to un minus k, this is known as right shifting. If I shift un to un plus k, this we call it as left shifting. So this change of origin, that's all. Left shifting theorem, right shifting theorem. We are ready to write two important theorems now. Here we write. So theorems are only for statements. Theorems, also known as shifting theorems. Pause here. In life, pause is also very important. Unless until you take a pause and look back what you have done carefully and go ahead with confidence. That is known as Simhavalokan. What this lion Sim does, it takes 10 steps and looks back with a confidence. What path I have encroached walked so far is very nice. I'll go ahead. So similarly, what we have done so far, you started with the definition of Z transform, n function to Z function. Found some basic transformation functions, u of n square, z of n square, z of n cube, z of n raised to 4, z of a raised to n, z of constant. So then got used to it by some example, z of 2 raised to n, z of cos n theta, z of sin n theta, hyperbolic n theta, z of a raised to n, z of phi raised to n. So now properties, slowly properties you are doing. One of the properties is shifting properties, that is we call it as theorem. What this tells is, property means if and then. If a n function has got this z function, then if at all I change this n to, if at all I change this n to n minus k, suppose if at all I change this n to n minus k, so what will be the corresponding change? The corresponding change is, to this u of z, you will have to multiply this change, extra z raised to minus k. So because you are making n minus k in the previous just talked to 5 minutes back, we call it as a right shifting theorem. So there are naturally two shifting theorems, right shifting theorem, left shifting theorem. For example, k equal to, I can write 1, 2, 3, 4, even 0 means same. Suppose if I write k equal to 3, okay, z transformation of un minus 3. So only k equal to, you have to write wherever k is there 3. So z transformation of that is z raised to minus 3. So 3 here makes it 3 here. Of course, this corresponding everything is changed into z transformation u of z as it is. Can you write some more for me? Z transformation of un minus 2. To the original u of z, you multiplied by z raised to 2 minus 2. Z transformation of un minus 10. To the original u of z, you have to multiply by z raised to minus 10. Z transformation of u of n minus 1. To the original u of z, you multiply by z raised to minus 1. So very similarly, instead of n minus k, if I write n plus k, you will get something different, of course, here. That becomes left shifting theorem. So that let us write left shifting theorem. Again, if z transformation of some n function is some z function, then what you will get? Z transformation of un plus k. So what will be the corresponding change? You will have to multiply, or you have to subtract. What will be the corresponding change? Let us see. This is the corresponding change, one corresponding change, and this remains the same, but inside again you have to go on subtracting u naught u1 by z minus u2 by z square, and so on. If it is k minus 1 is the last, uk minus 1 upon z raised to k minus 1. Let us get used to this by writing some k equal to 3, 2, 1. So z transformation of, for example, z transformation of un plus 3. So z cube to the function u of z, you have to go on subtracting u naught u1 by z minus u2 by z square. Stop it, because if it is 3, 1 less than that, you have to stop it here. Now this un plus 2 z square, because it is 2 here, to the original function u of z minus u naught minus u1 by z. If it is 2, you have to stop at 1. Stop it here. Z transformation of un plus 3. Just now we did un plus 3. Let us do un plus 1. Z raised to 1, because it is 1 here, 1 original function minus u naught, because here 1 less than 1 minus 1 is u naught. Stop here. So these two especially will be very useful for the examples point of view. So let us use this. So important examples are asked using these functions. Let us find some examples using these shifting theorems. So examples on shifting theorem. They are simple as well as important for your examination point of view. Don't forget, find Z transformation of, or show that Z transformation of this n function is e raised to 1 by z. Hence compute Z transformations of 1 by n plus 1 factorial. So un to n plus 1 shifting theorems, and one more, n plus 2 factorial. Let us get used to this. First of all, we are asked to find Z transformation of 1 by n factorial. But what is the basic definition of Z transformation? Summation un z raised to minus n equal to 0 to infinity. Every day once you should write this. Now instead of un, I'll write Z transformation of 1 by n factorial. So here also I have to write 1 by n factorial. Now I'll expand this summation. Go on putting n equal to 0, 1, 2, 3 and add them. For n equal to 0, z raised to minus 0 divided by 0 factorial. Both are 1. Plus, summation means you have to go on adding, plus 1 and 1 here. Z raised to minus 1 by 1 factorial. Z raised to minus 2 by 2 factorial. Z raised to minus 3 by 3 factorial. And so on and so forth, infinite series. Let me simplify and write in a better fashion. On the right hand side, 1 plus 1 upon z upon 1 factorial. Something square, 1 upon z square upon 2 factorial. Raised to 3 upon 3 factorial, and so on. But if you recall, what is e raised to x? 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on. And compare the right hand side here. If you compare these two here, exactly whatever x is there, it is 1 by z. So that means this expansion, this whole expansion converges to x equal to 1 by z. So let us write using the formula, wherever x is there, if you write 1 by z, wherever x is there, if you write 1 by z, e raised to 1 by z, you get. So we found z transformation of e raised to 1 by z. Now shifting theorem. What is z transformation of un plus 1? What is z transformation of un plus 1? It is, if it is 1, it is raised to 1. To the given function, you have to subtract u naught. Okay. So it is raised to 1 here. So, but what is un plus 1? Since this is our un, wherever n is there, n plus 1 makes us n factorial becomes n plus 1 factorial, and this we are asked to find, which is z into bracket u of z is, this is our u of z function. For 1 by n factorial in z transform, decoding it to z function, we get e raised to 1 by z, coded here. So that u of z is 1 by e raised to 1 by z. Now what is u naught? See here. un is 1 by n factorial. If you go on putting n equal to 0, 1, 2 and so on, n equal to 0, 1 by 0 factorial is 1. N equal to 1, 1 by 1 factorial is 1. N equal to 2, u2 is 1 by 2 factorial. That means it is 1 by 2. Suppose one more, u3, 1 by 3 factorial. That means what? If at all I know n function, no harm, no problem at all. I can go on finding u0, u1, u2, u3 and so on. So now I need u0 value, which is 1 by 0 factorial, which is 1. So I go back and write u0 value is 1 by 0 factorial, that is 1. So final answer for z of 1 by n plus 1 factorial is z as it is, e raised to 1 by z as it is, this becomes minus 1. Let us go to the next one, which is z of un plus 2 formula, which is according to the left shifting theorem, if it is 2 it is z square. To this u of z you are subtracting some things, u0, u1 by z, and stop, because if it is 2 you have to stop at 1. Now u0 already you found, u0 is 1, u1 is also 1. So using both of these I'll write z square, u of z is which we have found just now. This is our u of z, 1 by z. So instead of u of z I have to write 1 by z, minus u0 is 1 and u1 is also 1. So if I simplify z of un plus 2, so un is 1 by n factorial, un plus 2 is, wherever n is there, n plus 2, 1 by n plus 2 factorial. Noting this, if I write this as 1 by n plus 2 factorial, you can go up to n plus 3 factorial, n plus 4 factorial, no problem. This corresponding z function. One thing you noted here that we found only un, and afterwards using right shifting, left shifting theorems, we are finding next un plus 1, un plus 2, minus 1, minus 1 by z. Go ahead for un plus 3 without fail as a homework. Go ahead for it. Now similarly, suppose if I apply the same to same theorem to one more. Next example, important examples. If z transformation of n square, sometimes it is not given because you know it, z square plus z by z minus 1 whole cube. Find z of n plus 1 whole square. So un plus 1, z of n plus 2 whole square, and so on. Now let us write. So you are using here shifting theorems, don't forget, you are using here shifting theorems. Let us write un equal to n square. Let us note down that what are the values of un equal to n square. So let us note down the values of sometimes it takes time. N equal to 0, 0, n equal to 1, 1, n equal to 2, 2. So given the n function, you can go on finding corresponding u0, u1, u2. But corresponding, if at all you know, suppose only z function, coming directly here is difficult. Now given z of un, where in this case that un is n square, we know that we are used to it that it is z square plus z upon z minus 1 whole cube. Now we want z transformation of un plus 1, where the left shifting theorem tells that z raised to 1 to the original function. So this is our u of z, corresponding z function. You have to note down this. So now correspondingly the left shifting theorem, by shifting theorem we write to the original function we have to subtract some more values, because we have to stop here, because if it is 1, Here you have to stop at 0. Already we have noticed that u0 is also 0. If you find u0 is 0, then what is the answer? Z of un plus 1. So wherever n is there, n plus 1. Wherever n is there, n plus 1. If you make it, un plus 1 is n plus 1 whole square equal to z into u of z is here, z square plus z upon z minus 1 whole cube. Minus 0 because just now you found 0 here for u0. You have went on substituting to the given n function, n equal to 0, n equal to 1 and so on. So u0 equal to 0 you have to substitute. So correspondingly we got the answer of z of n plus 1 whole square is equal to z into z square plus z divided by z minus 1. So you can even go one step ahead to find directly also you can find, but using damping rule means you have to find like this. Sometimes you can multiply inside here to write z cube plus z by z square upon, no problem, z minus 1 whole cube. Now how about n plus 2? Z by z of, also we shall write also z of un plus 2 using shifting theorem. 2 means z square to the original function. You have to go on subtracting some u functions, u0, un by z, so on and so forth, but you have to stop here because it is 2 means 1 stopping here. So both u0 and un were found. u0 value 0, un value 1. So hence so I think after this example we shall stop. Hence here I have to write 0, here I have to write 1. So that finishes z transform of un plus 2 means n plus 2 whole square, z square into original z function. You have to write z square plus z upon z minus 1 whole cube minus 0 minus 1 upon z. So you can simplify this a bit, but no problem. You can go on writing as it is. You cross multiply and you can write as it is. So similarly, if at all you can find, please try this. If un is a sine of n theta, and you know the formula of this, find z transform of un plus 1. Find it without fail for me, please, without fail. So today we learned shifting theorems, and based on that some examples. Dear students, I'll end this but asking a question, a small question, and that will become a first part of next lesson. So given un equal to, for example, some n cube, you can go on finding u0, u1, u2, u3, because you have to go on substituting n equal to 0. Suppose n cube plus 2 I write, and something different, 0 plus 2, 1 cube plus 2, 3, 2 cube is 8 plus 2, 10, and so on. Now suppose I write some z function. Now what is the corresponding z function for this is, if I take the transformation, corresponding z function, okay, if at all I take some z function which is z cube plus 4z square plus z upon z minus 1 raised to 4 plus 2 upon 2z by z minus 1. From question is, suppose you don't know this part, read carefully, you don't know this part, but you know the corresponding z part. Can you come from here to here directly? Let me ask that question now. Suppose you know some u of z, which is something like z raised to 4 plus some z cube minus z square plus 2z divided by some z minus 3 raised to some 4. So can you come directly without knowing the un, corresponding un value? Can you come directly? What is u0, u1, u2, maybe up to u infinity, final initial value up to final value? Is it possible? don't know un, but directly from z function to corresponding u0, u1, u2, u3, because sometimes we don't want un, we want only initial values u0, u1, u2, u3 for our communication theory, for our signal processing. My dear students, answer is answer is answer is sorry answer is S. The answer is hidden in two theorems known as answer is yes for this. So two theorems which are known as initial value and final value theorems. So we shall take pause. With the next class, I'll be dealing with these two theorems and corresponding examples. So far from n to z we have done. Also we'll go from z to n back, which are inverse z transforms. Once you learn inverse z transforms, we can solve some differential equations. In discrete terminologies, they are known as difference equations, which become the base for your signals and processings. Till then, goodbye. Do the examples which I have given and take care. Bye bye.